Hello everyone, welcome to lecture series on real analysis. In the last lecture, we have discussed about the new topic which is Lebesgue outer measure, and we have seen the definition of Lebesgue outer measure and one property of it. So, third remark is let A is subset of R be countable, then M star of A is 0. It means the Lebesgue outer measure of the set A is 0 when my set A is countable. So let's try to prove this. First we have given that is my subset A, which is a subset of R, is countable. So let A is equal to the set and elements of this that set is A1, A2, A3 and so on. So here let epsilon greater than 0 be given, and we have to prove that the Lebesgue outer measure of A is 0. So for that we have taken some elements of the set AN which are in this open interval, right? Because the definition in the definition of Lebesgue outer measure, we have to take element from this open set. So if I am taking an from the open set an minus epsilon upon 2 raised to n plus 1 and an plus epsilon upon 2 raised to n plus 1, and the length of this interval is epsilon upon 2 raised to n. So thus A is subset of union of this open interval where my n is running from 1 to infinity. See here the sequence is in the interval an minus epsilon upon 2 to the power n minus 1 in an plus epsilon upon 2 to the power n plus 1. Here is an. If I am taking here an, then a1 is in the open interval is a1 minus epsilon upon, put the value of here n is 1, so epsilon upon 2 to the power 2, and here is a1 plus epsilon upon 2 to the power 2, right? So a1 is in this interval, likewise a2 is in open interval of a2 minus epsilon upon 2 to the power 3, and a2 plus epsilon upon 2 to the power 3. So here my set A is in this union of open interval. So hence, if I am apply here out Lebesgue outer measure will become m star of A, and subset will become in the form less than or equal to. So here use the definition. So summation over n is equal to 1 to infinity and the length of this open interval, and we know that here the length of this open interval is epsilon upon 2 to the power n, and apply the summation over this n. So we'll give the sequence 1 upon 2 plus 1 upon 2 to the power 2 plus so on. So sequence summation of this sequence, this series is 1, so left with epsilon. It means we have Lebesgue outer measure of the set A is epsilon. So thus m star of A is less than or equal to epsilon, and this is true for every epsilon greater than 0 here. So 0 less than or equal to m star of A less than or equal to epsilon, which gives the Lebesgue outer measure of the set A. Lebesgue outer measure of the set A. It means m star of A is equal to 0. So next property is m star is monotone. It means Lebesgue outer measure is monotone. Then let two subsets from the set A, that is A and B, a subset of R, be such that A is subset of here B. Then we have to prove that that is m star of A is less than or equal to m star of B. It means Lebesgue outer measure of the set A is always less than or equal to Lebesgue outer measure of the set B. When we have given that A is subset of B. So let's try to verify this remark. So for that, I'm taking m star B. It means Lebesgue outer measure of the set B. So is equal to, use the definition, that is infimum of the set, which is length of in, right? Summation over n is equal to 1 to infinity length of in. So this is whereas over the countable collection of open interval in R such that B is in the union of in, right? So let the sequence in be any countable collection of open intervals in R such that B is the in the union of this open interval, but we have given that the subset A is a subset of B, so that's why we can say that the A is also in this union of this open interval, because A is subset of B. Here B is in the union of this open interval, and also we have given that is A is subset of B. So that's why we can say that A is subset of union of this open interval, right? So from here we can say that the length of in, and then we take the summation, will always greater than or equal to m star of A from here. So thus we have this is true for one element A, and if I am taking wall set A, it will become summation over here is n is equal to 1 to infinity length of these open interval in will always greater than or equal m star of A. So this is true for any countable collection of open intervals in from R such that this is also true. So from this and this we can say that the m star of B greater than or equal to m star of A. It means Lebesgue outer measure of the set A is less than or equal to Lebesgue outer measure of the set B. Next one is the knot and the definition of translation invariant. So if I have the set A plus y, where my y is any fixed number, right? And the set A, we know that the set A is the subset of R. So if I am taking Lebesgue outer measure of the set A plus the element y, right? So the Lebesgue outer measure of this set will give Lebesgue outer measure of only the set A, means this is equal. So this property, we can say that this property is translation invariant. So translation invariant is what? The Lebesgue outer measure of the set A plus y is equal to Lebesgue outer measure of the only set A. Here we have to notice that this y is only the fixed number. We have to fix this y, right? So this property is known as the translation invariant. So let's see the remark 5 is m star is translation invariant. So instead of this, you have to ask in exam that prove that Lebesgue outer measure is translation invariant. So in that case, you have to prove this. It means m star is translation invariant. It means for any A subset of R, and let any y is in R, you have to prove this property, that is m star of A is equal to m star of A plus y. So let's see the verification. For that, we have take the sequence of the open interval, right, in R such that A is subset of this union of this open interval. And again I am taking the fixed number y from R. So note that the set A plus Y is what? So elements from this set in the form of small a plus y such that my small a is in the capital A. But this is subset of union of in plus y because I am taking this sequence in from the R, and also A is subset of this union, right? So all the elements are in this union. So that's why we can say that A plus Y is also in this the union. So here note that in plus y is also an open interval because here y is fixed and y is in, we have take from this set R, set of real number, right? And in is open interval. So in plus y is also an open interval in R, and this is true for each n. And moreover, this length of this in is equal to length of in plus y. This property we have learned in our BSc, right? This is true for the length of interval. So here we can say that this sequence in plus y is a countable collection of open interval on R, and such that a plus y is subset of union of this set of union, that is union of n is equal to 1 to infinity in plus y. So here if you take here Lebesgue outer measure, that is m star of a plus y, which is less than or equal to summation over n is equal to 1 to infinity length of in plus y. So is equal to, here we have the property, that is length of in is equal to length of in plus y. So from this we can say that summation over n is equal to 1 to infinity of length of in. So here we have that m star of a plus y is less than or equal to summation over length of in, and this is true for any countable collection in of open interval in R, such that A is subset of union of n is equal to 1 to infinity in. And Lebesgue outer measure of the set A plus y is less than or equal to Lebesgue outer measure of the set A. If I am taking for any set B, and next number, suppose I have choose the x instead of y, so x belonging to R. So from this we can say that Lebesgue outer measure of the set B plus x is less than or equal to Lebesgue outer measure of A, right? So now Lebesgue outer measure of the set A. So I am writing A as a plus y and minus y. We'll give A. So Lebesgue outer measure of A, m star of A is equal to, we can write that m star of A plus y minus y. But this is less than or equal to m star of A plus y, right? So this proved that m star of A is equal to m star of A plus y from here and from here. A less than or equal to B and B less than or equal to A will give A equal to B, right? So from this we can say that m star of A is equal to m star of A plus y. So next one is proposition. The statement is the Lebesgue outer measure of any interval is its nothing but its length. So earlier we were seeing that the Lebesgue outer measure of any set, right? Lebesgue measure of any set. It means M star of A, and we know that the A is a subset of R. So here, in this preposition said that the Lebesgue measure of any interval. If I am taking interval and find its Lebesgue measure, so this is nothing but it's the length of its interval. So for that, let I be in any interval in R, and we want to prove that the M star of I, it means Lebesgue measure of the interval I is equal to length of I, right? When L of I is length of I. So not that here I am taking interval I. It is either finite interval or an infinite interval. So first assume that the I interval I is equal to closed interval AB, and I am taking this element of this interval in the set of real number R, and with the property that A less than or equal to B. So from properties of the set of real number, we can say that for any epsilon greater than 0, closed interval AB is subset of this open interval, that is A minus epsilon by 2 and B plus epsilon by 2. So from here, if I am applying the Lebesgue measure for this side, we get Lebesgue measure of the interval, closed interval AB. It means M star of closed interval AB less than or equal to length of B. So M star of closed interval AB is equal to nothing but the length of this interval, and the length of this open interval is B minus epsilon plus B minus A plus epsilon. So this is true for here is less than or equal to not equal. So we have that Lebesgue measure of the closed interval AB is less than or equal to B minus A, and this is true for every epsilon greater than 0. We now verify that the Lebesgue measure of the closed interval AB is greater than or equal to B minus A. Right. So let the sequence In be any countable collection of open interval in R such that this closed interval is in the union of the open interval, right? So here we have to prove that the summation over n is equal to 1 to infinity of length of In greater than or equal to B minus A. So by Heine-Borel theorem, that the open cover In of the interval closed interval AB with, so here if we are using Heine-Borel theorem for that the open cover which we have denoted that In, where my n is running from 1 to infinity, of the closed interval AB. So it will admit a finite subcover. So it will admit a finite subcover. So if I am denoting this subcover as I1, I2 up to In, it's finite. So I am taking up to In such that our closed interval AB is in the union of the subcover, that is I1 union I2 union up to union In. So here we observe that the length of this open interval, and if I am taking its summation, is always greater than or equal to length of closed interval AB. So length of closed interval AB is nothing but B minus A. So here we know that the point A is in the closed interval AB. So A belongs into closed interval AB, and also we know that here that is closed interval AB is a subset of summation over of this finite subcover of the open sequence in, right? So from here we can say that the element A is in the uh, union of this open subcover. It means A is in I1 union of I2 union I3 up to so on union In. So from this thing we can say that A is in In for some I in the set 1 comma 2 comma n, right? So if I'm saying that the element I is in the interval I1 and I1 is denoted as the open interval A1 comma B1. So A is in open interval A1 comma B1. So from here we can say that A is in between A1 and B1. It means A1 is less than, strictly less than A, strictly less than B1. So if we have that b1 greater than strictly greater than b, so then strictly greater than b, so from here uh, a1 less than a, so we can say that b1 minus a1 is greater than b minus a. So b1 minus a1 is nothing but the length of interval I1, because I1 is open interval A1 b1. So length of this interval is b1 minus a1. So here we have write that length of I1 is greater than b minus a. So suppose b1 less than or equal to b, right? Here we have two cases. First case is b1 greater than b, and the other one is b1 less than or equal to b. So from that we can say that b1 is subset of this interval ab, and ab interval is in the union of this open subcover, right? So is B1 is does not belong into open interval AB1 because it is open. That's why B1 is not there. So from this it follows that B1 belong into IJ, but if here we have to remove the element 1. So this J is in between 2 to N here. This is without loss of generality, and next we can assume that this b1 is in the interval I2, and I2 we have denoted as a open interval A2 comma B2, right? So b1 is in open interval A2 comma B2. So from there we can say that A2 strictly less than b1, strictly less than b2, right? Now next term for the element b2. So here also we have two possibility, that is b2 greater than b1, right? So b2 minus a2 plus b1 minus a1 is equal to, you can see that b2 minus a2 minus b1 minus a1. So this is always greater than b2 minus a1, because here we know that a2 minus b1 is greater than 0, right? But b2 minus a1 is always greater than b minus a, right? So from here you can say that the b2 minus a2 will give the length of the interval I2, that is open interval A2 minus B2. So plus length of open interval I1, and we know that the length of open interval I1 is B1 minus A1 and is strictly greater than B minus A. So another possibility is B2 less than or equal B, right? So if we continue in the procedure, we obtain that in the interval I1, I2 up to IK, and such that the condition is A1 less than A less than B1, so A2 less than B1 less than A2 up to AK less than BK minus 1 less than BK. So it is clear that the above procedure must stop in at most n steps because we have finite elements n. So suppose that it stops at the nth step, which is bk greater than b. So for that nth step we reached at that L of ik, length of interval ik plus length of interval ik minus 1 plus so on length of interval I1. So it must be equal to bk minus ak plus bk minus ak minus 1 because the length of ik is what? Bk minus ak. Length of ik minus 1 is bk minus 1 minus ak minus 1 plus so on length of I1. Length of I1 is b1 minus a1. So which is strictly greater than bk minus a1. So here the reason, that is ak minus bk minus 1 is less than 0. So ak minus 1 minus bk minus 2 is less than 0. So that's why I can say that bk minus a1 and bk minus a1 is strictly greater than b minus a. So thus length of I1 plus length of I2 plus up to plus length of In is always greater than b minus a. And from this, if I am writing this length of interval in the form of summation, we get summation over k is equal to 1 to infinity length of ik is strictly greater than b minus a. So this proves that the sequence In is any countable collection of open interval in R. So from that we can say that closed interval AB is subset of union of this open interval In. So from then we can say that the summation over k is equal to or n is equal to 1 to up to infinity length of In is greater than b minus a. So hence we have that the Lebesgue outer measure of the closed interval AB is greater than or equal to b minus a. So this proves that m star of closed interval AB, it means Lebesgue outer measure of the interval closed interval AB is equal to nothing but b minus a, which is the length of the interval closed interval AB. So the second case is let I is the open interval and a less than b, it means a strictly less than b. So from that we can say that open interval is a subset of the closed interval AB. And if I am applying Lebesgue outer measure on both the side, we get Lebesgue outer measure of closed open interval AB strictly named, but less than or equal to Lebesgue outer measure of closed interval AB. But both gives the value of b minus a because m star, it means Lebesgue outer measure is monotone. So now if I am taking b minus a is greater than 0, hence there exists positive natural number k in the set of natural number n such that k into b minus a greater than I. So for all n greater than or equal to k, if I have a closed interval, that is a plus 1 upon 2 to the power n and b minus 1 upon 2 to the power n, will always contained in open interval AB. Next, from here, if I am applying Lebesgue outer measure from both the side, we get Lebesgue outer measure of this closed interval less than or equal to Lebesgue outer measure of the open interval AB. So from that we can write that b minus a minus 1 upon n is less than or equal to Lebesgue outer measure of the open interval AB, right? So from this we can say that if I am taking limit at n tends to infinity, we will get Lebesgue outer measure of open interval AB to AB is greater than or equal to b minus a. So thus Lebesgue outer measure of open interval AB, it means m star of AB will give b minus a, but b minus a is nothing but the length of the interval open interval AB. So it is not that for any two elements a and b from the set of real number with the property a strictly less than b, we can say that the open interval this contained in upper closed open and it is contained in the totally closed interval. So if I am applying Lebesgue measure to each, will give m star of open interval ab less than or equal to m star of closed open interval and is also less than or equal to m star of closed interval ab. So the length of open interval is b minus a and m star of closed open and less than or equal to m star of totally closed interval ab. So length of this will give b minus a. So here b minus a is less than or equal to Lebesgue outer measure of closed open interval less than or equal to b minus a. So this property gives the equation that is m star of closed open interval ab is equal to b minus a. So similarly, for the element a and b belonging to the set of real number r with the property a less than b, right, that is b minus a less than or equal to Lebesgue outer measure of the open closed interval ab less than or equal to b minus a. So thus Lebesgue outer measure of open closed interval ab is equal to b minus a. Right, this is true for interval which is finite. So our next case is suppose that my interval upon interval a is infinite interval, right? So if it is infinite, we have that any infinite interval which is open give delta greater than 0, right? And I will contain a closed subinterval j. And the length of open interval j is delta. So it's obvious that j is contained in the open interval I because it is infinite. So from that, if I am applying Lebesgue outer measure on both the side, will give m star of I greater than or equal to m star of j, but m star of j is 0. Why? My Lebesgue outer measure is measure, right? So this is true for every delta greater than 0. And here we have that length of any infinite interval, it's give the Lebesgue outer measure is infinite. So here m star of I is equal to infinite. It means the Lebesgue outer measure of the interval I, but here our interval is infinite. That's why it's give the length infinite, right? So this is nothing but the length of interval I, and our interval I is infinite. So its length is infinite, right?